Here we're going to look at the reducing ability of the halide ions. Now, halide ions have the potential to act as reducing agents. That is, they can donate electrons. They can do so according to the following equation, where X represents any halide ion. So they can donate electrons and they will form then the halogen, the diatomic halogen molecule. So these halide ions, we need to know about the trend in reducing ability as you go down group 7. So if we go from fluoride ions to iodide ions, and the reducing ability of these halide ions increase as you go down group 7. So the ability to act as a reducing agent increases. So reducing ability increases. Put another way, it's easier for it to lose an electron. And we can explain that because the iodide ion is the largest, and therefore the electron is more easily lost, or we should say lost more easily. So that's the trend in reducing ability as you go down group 7. It becomes easier for the halide ion to lose electrons. And this trend can be shown by its reaction with sulfuric acid. So reactions of halide ions with sulfuric acid. And this is quite a large part of the specification and can yield you quite a lot of marks. Now, these halide ions potentially want to give away electrons. So the sulfuric acid then is the thing that's going to gain the electrons. Sulfuric acid contains an atom which has got a high oxidation state. It's got an oxidation state, the sulfur's got an oxidation state of +6. Any species which contains an atom with a high oxidation state, such as this sulfur here, has potential to act as an oxidizing agent, has the potential to gain electrons and make this oxidation number go down. So this sulfuric acid, if it could talk, it would be saying, I want electrons. And it's going to want to get them electrons off these halide ions. The question is which halide ions is it going to get the electrons off? It's a fight for the electrons. In this reaction, the first thing that happens is we get a displacement reaction. Before any redox reaction occurs, this, I will stress to you, is not a redox reaction. When we look at the oxidation states, no oxidation state of any atom has changed. Sulfuric acid reacts with any halide ion, and these halide ions are in the form of sodium salt. So NaX represents any sodium halide, sodium fluoride, sodium chloride, sodium bromide, or sodium iodide. And what we get is, all that happens is that a sodium here takes the place of one of the hydrogens in sulfuric acid. So we get NaHSO4 and we get HX. So that's the first thing that happens. And be aware that one of the observations of this reaction, the first thing you'd observe, this is observed as white, misty fumes. And that's the case whether this thing here is HF, HCl, HBr or HI. This first reaction, this displacement, happens with all halide ions. The next step in the reaction of halide ions is sulfuric acid is where we get a redox reaction occurring. Now, again, what we said is this sulfuric acid, it wants electrons. It's got an atom with a very high oxidation state here of sulfur, oxidation state of 6, and that sulfur could potentially, that oxidation state can decrease by gaining electrons. Now, it's got 4 halide ions that it could potentially gain electrons from. So you've got the fluoride ions and chloride ions. Now, when sulfuric acid comes in contact with the fluoride ions and the chloride ions, it's basically asking, give me your electrons. It's asking the fluoride and the chloride ions to give me its electrons. But these fluoride and chloride ions here, they hold on to their electrons very tightly because fluorine and chlorine atoms are very small. So the nucleus has got a really strong attraction for its electrons. So basically they are poor reducing agents. That is, they do not want to lose their electron. Okay? They hold on to their electron too tightly. So when sulfuric acid meets the fluoride and the chloride ions, there is no reaction. There is no redox reaction. We can say it another way, that basically fluorine and chlorine are better oxidizing agents than sulfuric acid. That is, that fluorine and chlorine want the electron more than the sulfuric acid does. So when this fluorine and chlorine have got the electron in the form of the fluoride and the chloride ion, they're not going to give their electron to sulfuric acid. So there'll be no redox reaction with fluoride ions and chloride ions. There'll be no reaction. The next halide ion is the bromide ions. Now, the bromide ions are bigger ions. The electron that's going to be lost is much further from the nucleus. So when the sulfuric acid comes along and asks the bromide ion, can I have some electrons? The bromide ion will give the sulfuric acid electrons. The sulfuric acid is a better oxidizing agent than bromine. That is, the sulfuric acid wants the electrons more than bromine does. Now, what happens then is, this is the reaction then of bromide ions and sulfuric acid. Now, the first thing we're going to do is when we look at a reaction of bromide ions and sulfuric acid, we've got to look at the half equations. Now, when bromide ions are oxidized, they do so according to the following equation. And we said this earlier on in the video. We get Br2 and 2 electrons. So the oxidation state of the bromine here is -1 and it's increased to 0, so we've got an oxidation. Because this reaction is an oxidation, we call this thing here the oxidation product. The product formed from the oxidation half equation. The sulfuric acid, you simply need to remember that the only thing that the bromide ions can reduce sulfuric acid to is sulfur dioxide. What you're going to get then is the sulfur is oxidation state +6 and it will reduce it to +4. Now, you need to write a half equation for this given the reactants and the products. So this is going back to redox. Now, the first thing we do is balance the atom undergoing redox, which is the sulfur. We can see there's 1 sulfur on either side. We then need to balance any oxygens with water, where we can see that I've got 4 oxygens there, 2 oxygens there, so I need to put 2H2O is my products. Now, I then need to balance my hydrogens with hydrogen ions, and we can see now I've got 2 hydrogens on this side, but I've got 4 on this side, so I need to put 2H plus. And to balance charge, I need 2 electrons. tidy that up a little bit. So that now is my half equation for the reduction. And because this is a reduction half equation, we would call this thing here the reduction product. It's what's produced from the reduction half equation. Now, this SO2 is observed as a choking gas. Just to let you know that the Br2 is usually an orange liquid, but sometimes orange fumes as well. Okay, so we can combine those two half equations to give an overall equation, and that is then H2SO4. We can see hopefully that the electrons cancel 2 electrons there, 2 electrons there. So we can write an overall equation, H2SO4 plus 2H plus, they're the reactants from my reduction, plus 2Br minus, and that reacts to form SO2 plus 2H2O, they're my products from the reduction, and we've got Br2 from the oxidation. So that would be my overall equation for the reaction of sulfuric acid and bromide ions. So the sulfuric acid wants the electrons more than bromine, will take the electrons off the bromine, and the bromide ions then are reduced to, oxidized to bromine. Now, the next halide ion is the iodide ions. The iodide ion is the best reducing agent of all. It wants to lose its electrons more than anything. So what iodide ions will do, they will reduce this sulfur here even further. That is, it will give it even more electrons and make this oxidation state go down even more. Now, when iodide ions react as reducing agents, it's exactly the same half equation as the bromide ions. It's oxidized to iodine and then 2 electrons. Now, potentially these iodide ions could reduce the sulfuric acid to SO2, and we'd get exactly the same half equation here. The iodide ions could do exactly the same. But there is an additional 2 reduction half equations that we need to be aware of. The sulfuric acid could also be reduced to sulfur, S. Now, I'm not going to go through the ins and outs of the half equation for this. It's something that you need to be aware of. But what we would get here then is we would get 6H plus 6 electrons. And that would give us then sulfur plus 4H2O. And hopefully you can see that everything balances there. Again, we can check that it's 6 electrons. Oxidation state of the sulfur is plus 6, and it's gone down to 0. So this sulfuric acid, this sulfur, has gained 6 electrons, go from plus 6, gained 6 electrons, and it's gone to 0. If we were going to combine this, and again, I will just mention that this is another reduction product. It's another reduction product, and that is observed as a yellow solid. The iodine, by the way, is again an oxidation product. This is usually observed as a black solid, or sometimes purple fumes. The purple fumes are formed because the reaction is exothermic, and the heat generated will cause the iodine to sublime into these purple fumes. Now, another potential reduction, the iodide ions will give even more electrons to the sulfuric acid, and it can reduce the sulfuric acid even further. Another potential reduction equation we can get is where it reduces the sulfuric acid to hydrogen sulfide, which is H2S. So we get now H2S and four H2Os. And again, hopefully you can see that it all balances. We've got an oxidation state here of +6, and now it's gone down to -2. So +6 to -2 is an 8 electron change. Now what you should be able to do is, I'll just let you know that this is a bad egg smell. It's horrendous. It's one smell never forgotten. It's not anything that you want to be doing in a lab on a hot day. It's horrendous. Not very nice. Now, you should be able to combine the oxidation and the reduction half equations. You would need to multiply the blue equation, the oxidation half equation, by 3 if you're making sulfur, and you need to multiply by 4 if you want to make H2S. So let's just have a quick look at these. So you'd get H2SO4 plus 6H plus, and then it would be then 6I minus. And this is if we want to produce sulfur as a product. That would give you sulfur, 4 H2Os, and this time we would now get 3I2. So that's the overall equation if sulfur is the reduction product. If H2S is my reduction product, then we would need to times the oxidation half equation by 4. And this time I get 8I minus. And that then gives us H2S plus 4H2O plus 4I2. So there is quite a long video there on the reducing ability of the halide ions. Remember the trend, that is they become better reducing agents as you go down the group. And then remember the reactions with sulfuric acid. The first one is this displacement reaction. Remember this occurs with all the halide ions. Okay, remember then with the redox, which is the second part of the reaction, the fluoride and the chloride ions, they hold onto the electrons too strongly, so there is no redox reaction which occurs with fluoride and chloride ions with sulfuric acid. The bromide ions will reduce the sulfuric acid to SO2 only, and that is seen as a choking gas. Remember that the SO2 is a reduction product. The bromine, which is an orange liquid or orange fumes, is an oxidation product formed from the oxidation half equation. Iodide ions, there are 3 potential reduction products there. It will also reduce the sulfuric acid to SO2, exactly the same half equation. But we can also reduce sulfuric acid to sulfur, where sulfur is another reduction product seen as a yellow solid. You can also reduce the sulfuric acid to H2S. H2S is another reduction product with a bad egg smell. The iodine is an oxidation product seen as a black solid or purple fumes. And then once we've got these half equations, we should combine them to give the overall redox equations highlighted there in yellow. If you have any issues being able to balance these half equations, then you should go back and look at one of the early videos done on redox. And that is the reducing ability of halide ions.